Okay, perfect. All right, go ahead.
All right, cool. All right, so I'm going to be going over compile time versus runtime. As for like importance on this topic, I would say it's probably not as important as some of the other things you're going to learn in this presentation. However, it is still a good thing to know and understand. And after the midterm, it's going to become a lot more useful later. So understanding the distinction will become a little bit more important, but it's still a good thing to know. Okay, so Java is a compiled language. So if you recall from lecture, or Professor Hug put up like this diagram. So essentially we start with some sort of source code, and this is what we make. This is what we type into. This is our like hello world, our public static void main. This is where we write our code. After we write our code, we compile it, traditionally using the Java-C command line. And what this does is that it takes our code and it converts it into a bunch of like illegible bytecode. But this bytecode is interpretable or readable to the machine. So after we get this bytecode, which is in the form of a class file, we then run it through a Java interpreter using the Java command line, and then that's when we get our stuff happening. And what's important here is that we really have two different events, right? We have our compile time, which occurs when we run Java-C, and we have our runtime, which occurs when we run Java. When we first run with our compiler, we catch different types of errors at each stage. So when we first compile, we catch type errors and syntax errors. So for those of you who've used IntelliJ, this is when you get like those red underlines, right? So a syntax error is something like forgetting a semicolon or forgetting like a curly brace at the end of a function or something like that. So those are all caught by the compiler, and it makes debugging a little bit easier. As for the interpreter, it catches more of these exceptions, right? So maybe you're like operating on a linked list and you have some like null pointer exception, for example. So these are things that aren't going to be caught by the compiler, but are going to be caught by the interpreter when you actually run your code. Yeah, any questions on this stuff? All right, cool. So just as a quick practice question. So Alice runs Java-C some file on the command line, but receives an error. Which of the following could be wrong with her code? Just take a minute and think about it. All right, does anyone want to volunteer an answer? It's okay if it's wrong. Yeah. Yep, that's exactly correct. So if we go through each option, a null pointer exception is something that's caught by our Java interpreter after we compile, so we run the actual Java command. So if you've worked with like int lists, for example, you may have run into this issue a bunch of different times. The second thing is an infinite loop, and this isn't like you'll get like a Stack Overflow error. And again, if you just have like while true or something, the Java compiler isn't going to catch this because it's neither a syntax error or a type error. And then C is correct exactly because it is a type error. We're like creating a function that's supposed to return type A, but actually returns type B. So the Java compiler is going to catch this, and you would get like a red line like in IntelliJ if you were to try to do this. And then D, a divided by zero error. This is actually an exception. So if you type in print one or system.out.println like 1 divided by 0 in a Java file, you're not going to get an IntelliJ error. It's not a type error or a syntax error. You'll get like an arithmetic exception. So yeah. So yeah, the answer is C. Oops. Yeah.
So next, we're going to be looking at pointers and references. And what exactly is a pointer or reference? So a reference, oh, I'm sorry, I think that's blocking it a little. A reference in Java is essentially a memory address that shows exactly where an object's variables and methods are stored. So in this short example, what we're doing here is we have this new dog object with name Fluffy and age 3, and we're assigning it to a variable Fluffy. And this bubbles variable is also pointing to Fluffy, but Fluffy's pointing to this new dog object. So both Fluffy and bubbles are both pointing to this dog object. So now we're going to try and change the name of Fluffy to Buster. And so when we print out Fluffy.name and bubbles.name, we're going to be getting Buster for both of them. This is because both Fluffy and Bubbles are variables that are references to the new dog object that was created. They aren't the actual dog object themselves. So let's kind of solidify that understanding with an exam question. I'll give you guys like about 3 minutes to discuss this with your partners or in pairs and see what you guys come up with. Sorry. Yeah, I think a student must have posted the link to the slides in Ed. But if not, I guess you can take, oh, it's on there? Okay, perfect.
In the chat.
The chat?
Just want to make sure to ask questions. And Shanani's there. You can get the co-host.
Okay.
Oh, never mind. Go ahead. Okay.
So there's a question that says, does Bubbles point to the same dog as Fluffy? And yes, in the previous example, oh, whoops, can I go back? Okay, I don't think I can go back, but yeah, so essentially Bubbles will point to the same dog object as Fluffy. Okay, I hope you guys got somewhere with that. But I'll quickly go through how exactly you'd probably want to approach this problem. So I guess first things first, we have our code there, and we can see that the first 3 lines, we're creating 2 2D arrays, A and B. Whoops. 2 2D arrays, A and B, and then one 1D array, C. So if we draw those out, we have an integer or 2D array with like 3 rows and 2 columns. Pictorially, based on what we have, like just got to draw the pointers like this because there are 3 boxes here. So we have our A variable pointing to this one, our B variable pointing to another 2D array, and our C variable pointing to this new integer array with values 1 and 2. Now, the next thing is we have a for loop and then a for loop within that for loop. So the outer for loop, we can see with the variable I, it goes from 0 to 3, excluding 3. So it'll go like 0, 1, 2. And the inner for loop, J, goes from 0 to 2, excluding 2. So it'll only go like 0, 1 before moving on to the next iteration. So I think I'll just show you guys all the different iterations that those 2 for loops would like result in. So when I is equal to 0 and J equals 0, we're going to have A at 0 equal 0 plus 0. And then we increment J by 1. So A at 0 at 1 is equal to 0 plus 1. And then because if we increment J again to get 2, 2 is not less than 2. So we exit the for loop and go back to the outer for loop and so on. Like the whole process repeats until I is equal to 3 and we exit that for loop. And to draw this out pictorially, A at 0, we have like we have another array with 2 spaces in it, and it will have 0 and 1. A at 1 will have an array containing values 1 and 2, and A at 2 will contain values 2 and 3. And then moving on to the next for loop, where the variable I appears again, but it goes from 0 to 3 again, so 0, 1, 2, excluding 3. And here, what we're going to do is assign B at whatever value I is equal to A at I. So B at 0 will equal A at 0, B at 1 equals A at 1, B at 2 equals A at 2. And we can draw this pictorially by using like these arrows. So B at 0 points to the array which is being stored at A at 0, and so on. And then for the final step, we have A at 0 at 1 plus equals 1. So A at 0 points to this array here, and at the first index is this value 1. So we increment that by 1 to get 2. And now we're just printing out what we can see from this diagram. So B at 0 at 1, so we go to this array, B at 0, which points to this array, and then at index 1 is this value 2. And then next, A at 1 equals B at 1. Now this has a Boolean value, like as an answer, because we're trying to see whether A at 1 equals to B at 1. So if we go to A at 1, that points to this array over here. And B at 1, we go to follow the pointers, I guess. We go to this array, and then at 1, we point to this array. So essentially, because they're both arrows are pointing to the same array object, they're equal, so it's true. And then for A at 1 equals C, if we go at A at 1, so this integer array, and then go to the first index, which points to this array, and look, even though the values 1 and 2 are the same as the values here in C, 1 and 2, because they're not the same object, they're not equal to each other. So the answer is false. Does anybody have any questions related to this problem?
I don't get the AI. I don't get the AI.
The AI?
Yeah.
In the for loop.
The second for loop.
In the second for loop? Okay. So B at I equals A at I?
Yeah.
Okay. Let me see if I can go back. So what exactly do you not understand about it? Is it the assigning the index?
What is the AI exactly point to in that diagram?
Okay, so when I is equal to 0, A at 0 would be this, whatever this index is pointing to. So in this like integer array over here, the first index, which would be like 0, I guess, because everything is 0 indexed in Java. So that points to this array over here. So that's the A at 0. And then we essentially assign B at 0, B being this integer array,
got it. Thanks.
and then assign that. Yeah. Does anybody else have any? Yeah.
Yeah, I have a question on the first statement. How does B have access to value if we assigned it earlier in the later for loop? We assigned B 0 to A0, so it points to 0 index or 0.
Yeah, so basically it's pointing to the integer like array that contains the value 0, 2. So not the value itself, but so B at 0 points to the, wait, hold on. So B at 0 points to like this integer array index 0, so this one, and that arrow from that index is pointing to this particular integer array. So this integer array itself is B at 0, but then B at 0 at 1 will be the 1 index in that integer array. So that's why it gives the result 2 and not 0. Yeah.
second print statement, it would still hold true if instead of like a 2D array, the arrays will follow primitive values.
So you're saying like A at 1 say is equal to 1 and B at 1 is also equal to 1?
Yeah.
And they point to like the same integer array, same index?
Or would it just like copy the integer but like not the address itself? Or
Okay, so if A and B were pointing to two different integer arrays and A at 1 was equal to 2, or let's say choose another value, A at 1 equals to 3, and B is pointing to another integer array, and B at 1 also equals 3, then they wouldn't be equal to each other because they're pointing to two different objects.
so
Is that right? Or is it?
Do you mean like if you set them, if you had like a of such equals B of such and they were both, yeah, it would read them as integers and it would say that they're equal.
Oh, sorry. Yeah, they could be 3 and 3, they'd be equal then. Apologies.
But if I have two arrays that are, but two different arrays, but the same entries, so both integer arrays technically all, let's say 1, and then I compare them, then it wouldn't say that it's the same because the point is different.
That is true, yes. If you're comparing integers, so if you're saying like A of 0 and B of 0, those are integers. If you're comparing arrays A and B and they're different pointers, unless you have a specific function, like, you know, dot equals the string that like will check to see if all the entries are the same, we'll say that they're different because they have different pointers in memory.
so
like,
what if it's like so like this equals it would be true if it's just recruited, right?
Yeah.
So what if
Or if they're in the same memory.
Okay, yeah. So like what if they were like the integer class like or something like that? So kind of as an object.
What do you mean integer class?
Like capital I.
I believe that's a primitive, but if it weren't, then not necessarily. So this kind of gets into or which term it is, but like if how we define equals under certain things. So there's not like a straight answer to that, but generally if something's a pointer and not a primitive, it will only like equals will only give you true if they're at the same memory location. Yeah, but hypothetically you could like define some equals and maybe override that. But yeah.
Just some like questions in the chat. When they say what does it mean when you initialize a 2D array without a second value in the second box? I'm not too sure about that one. I think it's just like whatever space is assigned in the like memory. It's not given like a certain like space until it's populated.
I'd say I think Java does give the space. It would initialize everything to 0, I'm pretty sure.
Okay.
Yeah, it would be different if we're talking about C, but in Java that's what's going to happen.
Okay. And A at 1 equals B at 1 mean they have the same memory address or same contents?
Same content.
Same contents, yes.
When you say initialize everything to 0, does that mean if an empty array inside this array is actually 0?
We're talking about if you say like you want to say int array of B equals like int of 2, you'd get like 0, 0. Is that what you were asking?
That second line where they initialize the 2D array, they don't specify the size of the second array. So it would just be an array of size 3 with just empty arrays starting, right? And then we would reassign pointers.
Right. Yeah, that's correct.
Just clarify.
And if we were to do A at 1 dot equals C, would it return true? I think it would still return false because it's still not the same object.
Yeah,
Is that right?
I mean, so it depends. I'm not entirely sure what the dot equals method is in array for Java. If it's defined, then yeah, if they're the same thing, even if they're different pointers, it will say true. If it's undefined, then I mean, it'll either tell you I don't know what to do with this, or it'll take its parent class, which will probably say no, they're not equal unless it's the same pointer.
I think I think it checks the equals sign, check equivalence, or the same value. I think it checks the equivalence, so whether it's the same object or not. And then with strings, obviously you'd have to use dot equals.
Right, because different strings are going to be stored in different places in memory. Exactly.
And making an array of dimensions 3 would create a size 3 array with every element being a size 2 array. Yes, that's correct. Okay.
Yeah, to answer your question, if you have two integers that are like capital integer, like the wrapped, like using the wrapper class, if they both have the same value, like equal return false.
Oh, okay, interesting. I didn't know that.
Yeah, it's interesting because like if you said it like I equals j,
Right. So it's not a primitive.
exactly. But if you said I equals like 3, like the actual value, it checks true.
Interesting. There you go.
Yeah, and then also just one last question is, are we required to fill out all the boxes if we were given this problem on the exam? You don't need to fill out all the boxes. They're just there just in case you need them, but you should do what you think is right. Yeah. And exam logistics, I'm not too sure about.
Oh,
I had a quick question for B.
Yes.
Oh, yeah, we're not in charge of that.
Okay.
We're
Yeah.
not core staff.
Yeah, we're not. Okay. Cool. Does anybody have any more last questions for this?
Yeah. For the
Perfect,
int
thank
array B, yeah, how come you have 3 sets of boxes if it's a 2-dimensional?
All right, so in this mini lecture, we're going to be learning about both singly linked lists as well as doubly linked lists. This is a really important topic because it is kind of a fundamental topic that lots of other topics are going to build on when we look at the practice problems. So for example, you might have a recursion question that is asking you to implement a linked list recursively. So it's very important to understand the building blocks before we work our way up. We're also going to be looking over sentinel nodes as well as DEX, which is a more complicated version of a doubly linked list. All right, but first of all, let's start by analyzing the singularly linked list, which we should have some familiarity with from CS61A. This is a linear data structure that consists of multiple nodes being linked together. Each node contains 2 pieces of information. The first is a data field, commonly referred to as a node's item or head, and the second is a pointer to another node referred to as next or tail. The diagram below shows an example of a singularly linked list with 3 nodes. The first node contains an item X and a pointer to the next node. That node contains another item, Y, and another pointer to the third node. And the third node also has the item Z, but it does not have a next pointer, right? That slash to the next box is a shorthand for null, which you should remember for the test. That means the third box is the end of the list because there is no box which follows it. Now let's take a look at doubly linked lists. There's only one difference, though it is an important one. A doubly linked list contains a pointer to both the next node in the list as well as the previous node in the list. And the distinction here is that in a doubly linked list, our individual nodes know both what comes after them as well as what comes before. This means that we can traverse both ways through our list, whereas in a singly linked list, we can only traverse one way. And so let's break down what that means, right? If we find ourselves in the, sorry, can everyone be muted? All right, let's break down what that means. So if we, okay, wait. Sorry, no, you're good, you're good. Okay, everyone should be muted, cool. Right, so if we start ourselves in this singly linked list and we look at the Y node, a second. In this node, we have no way of knowing what nodes came before it, right? We can access the item in this node, which is Y, and we can also access the X, which points to the next node, which contains the item Z, but we have no way to go backwards, right? If we're inside of the Y node, there is no way to know that an X node came before us. However, in a doubly linked list, if we were in the B node, we can know what the item is, what node came after us, and what node came before. And so this is very different from arrays that you might be familiar with in CS61A, because we cannot access any piece of information we want just through the index of the item. We need to traverse through our list by repeatedly going to the next node. And so here's a very bare bones implementation of the nodes for singly linked lists as well as doubly linked lists. As you can see, there's only one important difference, that being that doubly linked lists contain an extra value called previous. And so if you're asked a question on the test regarding linked lists, this is the implementation they will most likely be using. So familiarize yourself with it, but it should also be provided to you on the test. So let me pause here. Does anyone have any questions about singly linked lists or doubly linked lists? Yes, of course. Sorry about that. All right, let's talk about DEX, which is short for double-ended queues. These are a special type of list that commonly implements 4 main functions: add first, add last, remove first, and remove last. Hopefully all those are pretty self-explanatory just from the names of their functions. And so while you can implement these functions for just any old list, decks are really special because they can run these functions in constant time. And so if you want to implement a deck using linked list, you're going to have to use doubly linked list. And let's think about why that's the case, right? Let's think about what would happen if you try to implement add last using singly linked list, right? You would start at the beginning of the list and you have to travel through the nodes until you reach the last node. And you would be able to tell that this last node is the last node because the next is empty, right? And so at that point, you're going to add the next item to the end, right? However, if you have a very, very long list, this is really inefficient, right? Because you have to iterate through every single node in that list in order to get to the end to run add last. And so decks get around this problem by using doubly linked list and a thing that we call a sentinel node, as you can see right here, right? This sentinel node is like any other node, except that its item value is arbitrary and its previous points to the last node in the list, and its next points to the first node in the list. And so this means that when you call sentinel.previous, you're accessing the last node in constant time. And when you call sentinel.next, you're accessing the first node in constant time. And so I stole this image from Professor Hug, and I strongly recommend taking a screenshot of it because it is very helpful. And this is a bit of a complicated topic, so if anyone has any question about this, please let me know. Or if I'm going too fast, let me know again.
Might be a good thing to include on your cheat sheet.
Yeah, so as this person says, how do you go backwards in a doubly linked list in chat? Yes, it is using .previous as so the person answered. All right, cool. So let's work on a practice problem. So the text of this problem is shown on the right here. In the 4 blanks besides the print statements above, write the result of the print statement. Oh, sorry, I didn't see it. Yeah. Yeah, so if you, right, yeah, I understand the question. So like, if we're in this 9 node right here, and then we call .previous.next, so yeah, you would just be back in the 9 node again, basically. Yeah. Sorry, so if we're at the 9 node, 9's previous is the 3 node, right? Yeah, and so if we called next on that, it would go back to the 9 node. But that works for like any node, right? So like 3, if you called previous, it goes back to the sentinel node, and if you call next, it goes back to 3, right? So .prev, .next just cancel each other out.
If I want to reassign node to next, I do.
Wait, sorry, can you repeat that one more time?
Can you like use that and then it seems Jake that we can use like previous next to decide what next is.
Yeah. So, oh, okay, I kind of understand what you're saying. So it's like you're trying to say 9 node.next equals 9 node.prev.next, right? Okay, yeah. So definitely you could do that. If you wanted to do that though, you could just say 9 node.next equals 9 node. Right, you could just cut out the prev.next, but that is totally like legitimate. You could do that. I just don't quite see the purpose for it. Audrey Sue has a question in chat. What is the benefit of a sentinel node? So the sentinel node is something that we are always able to access, right? And the sentinel node keeps track of what is the last one as well as the first node in the list. And so you might be asking yourself, you know, why do we even have a sentinel node, right? Like, why not just point at this 3 node, for example? And the reason why we do that is if we want to do remove first or add first, it's a lot easier to have a sentinel node just when we're implementing the deck itself. Because if we wanted to remove this, then we have to change like what the sentinel node is, and we'd also have to change like all the corresponding things. So just having a sentinel node here, it helps like streamline the process, I suppose. It's mostly just for implementation. You're not going to have to really know that on the test.
Another reason is you don't have to have like special cases for null exception errors in certain places. So, you know, you want to add first and you want to add first to like the first part of an existing first node, but the existing first node is null, that's a problem. We have a sentinel node that we don't care about the value of. It's just a kind of a placeholder for a null where it's not actually null and we can add things to it without getting errors, but it's not actually part of our list. It just means that we have less exceptions we might run into. We have less if cases that we have to think about. It makes our code cleaner.
All right, any last questions on this? All right, great. Let's take a look at this practice problem. So the text of the problem is as follows. In the 4 blanks besides the print statements above, write the result of the print statement. Oh, let me move this real quick, sorry. Oh, That does not move. Okay. In the 4 blanks beside the print statements above, write the result of the print statement. The answer to the first one is already provided for you. And so they've also provided implementation for the int list here. And as you can see, Professor Hug really likes to use head and tail. It's also often item and next, but it's basically the same thing. And you can read this text here. I'll give you guys a minute just to start thinking about it, but we'll go over it step by step anyways. All right, so let's start working on this solution here. The first 3 lines are pretty self-explanatory, right? A, we're creating an int list called A that has a head of 5 and a tail of 0. And then we're also creating an int list B that has a head of 9 and a tail of 0. And we're just printing A dot head, which is just 5, right? As you can see in this diagram here. This next line is a bit more interesting, right? So we're creating this int list C, and we can tell that there is a first node here that has head of 1. But what exactly is its tail, right? Well, we're creating another int list, actually. We're creating another int list that also has a head of 7. And this tail, in fact, is going to be a pointer, which is pointing to int list B. That's why we draw this arrow here. On the next line, we're going to say A.tail is equal to C.tail. So what that's telling us is that the pointer in A.tail should be pointing to the same place that C.tail is pointing to, which is why we draw the arrow like this. And then we do A.tail.tail, which is equal to B. So A.tail is this box right here, right? And A.tail.tail is this box right here. And so we're saying that the pointer in this box should point to B, which it already is. So this piece of code is actually kind of like a trick, right? Then B.tail is equal to C.tail, right? So these two are just pointing in the same direction. And now let's take this step by step, right? Int list D is equal to new int list 9001 B.tail.tail, right? So immediately we're creating this outside, right? We have 9001 as a head, and then we have a tail that we're going to figure out what it's pointing to. What exactly is B.tail.tail? Well, we start at B.tail, right, which is this box. And then we go to B.tail.tail, which is this box. And so the D.tail should be pointing to the same place that B.tail.tail is pointing to, which is pointing to int list B, right? And so now can anyone tell me, that just gives it away. Okay, well, that kind of gave it away the answer, but the answer is 9. And so let's take this step by step, right? D.tail.tail.tail.head is equal to what? We start at D.tail right here. Then we go to D.tail.tail, which is here. D.tail.tail.tail, which is here. And so this pointer is pointing to int list B right here. And so head is going to be equal to 9, right? Then system.out.print line A.tail.head, right? A.tail is right here. So A.tail.head is 7. And so C.tail.tail equals C.tail is a bit interesting. So let me give you guys like maybe 20 more seconds just to think about what exactly is happening here. All right. So C.tail is right here, and C.tail.tail is right here, right? And so we want to set C.tail.tail, the pointer here, equal to C.tail, the pointer here, right? And so what we're doing is we actually created a loop, right? This box is pointing towards itself. C.tail, C.tail.tail's tail is C.tail, right? And so this is another unique thing about linked lists is that we can have loops in them, right? And we're going to see that right here with A.tail.tail.tail.tail.head, right? What exactly is happening here? Well, we start at A.tail, and we realize that A.tail is this box, right? And A.tail.tail is also this box. And A.tail.tail.tail, that's 3 tails, is also this box. And so you realize this is creating a loop, right? And so no matter how many tails we have in here, ultimately .head is going to be 7, all right? So does anyone have any questions on this question? Is there an infinite loop here which will cause seg fault? I do not. Is there an infinite loop here which will cause seg fault? I don't believe there is, no.
No, it won't cause seg fault because it's not taking any more memory. The memory is just the amount of lists we have, which is 4. It's not that much, so it won't seg fault ever.
Yeah.
Unless you have like a teeny amount of memory to the point where you can't store 4 linked lists. At that point, you need to get your computer checked out.
And another question here is, are int lists SL lists? So SL list is just referring to like a type of data structure, right? And so in this specific case, we define a class called int list that has both a head and a tail. And so yes, in this specific case, int list is a single linked list.
Not in the way Hug implements it. I would call the int list more like int node. This is probably a Hilfinger test, in which, you know, the names are slightly different, but these are int nodes basically. So yeah, it's a part of I mean, SLLs, like he was saying, is the same idea as that. Only part is that it includes these int lists, also called int nodes, but also has things like size, which an int node does not have. So yeah, practically the same thing though, but not quite.
All right.
Can you talk again, like why the head of D is 5?
Why the head of D is 5? Oh, that's because I copy pasted the wrong thing. It's 9001, my bad. All right, cool. Moving on to the second practice problem. All right, so we have the deck interface as array deck and linked list deck. And so now we're going to improve the deck interface by adding a new default method. So our job is to add a default method, remove item X, that removes all items equal to X. And this method should return true if anything was removed. It should return false if nothing was removed. You may not use a new keyword. And if you need to determine that 2 items are equal, use the dot equals method. And we have all of these 8 functions right here, where we have add first is empty, print deck, remove first, add last, size, get, or remove last. Let me give you a couple minutes just to think about this yourself. All right, so let's kind of walk through what my thought process is, right? So immediately I'm seeing a size function here, which is very useful because we're going to have to iterate through every item in this deck and check if those items are equal to X, right? And I'm also seeing this get function right here, which is allowing to use the index. So right now I'm kind of thinking to myself, well, I should just use a for loop to iterate through every single item in this list, right? And so that code would kind of look like this, right? We got an int size equals size, and we do for int I equals 0, I less than size, I plus plus, item temp item equals get I. And I run into a problem, right? And the problem is, even if I have the index and I know what item is at the index, I can't remove the item at that index, right? My code only has a function to remove the first and the last items. So none of these provided functions do what we want. And so if this is also your thought process, I'm going to give another maybe 30 seconds to kind of rethink and approach this problem from a different way. All right, and so this is a solution right here. We were right, actually. We are supposed to use size in order to create a for loop that iterates through every object. However, what they're doing is kind of interesting here, right? We have an item which is first, which is equal to remove first. So we're basically removing the first item and storing that temporarily. And then we're checking to see if that item is equal to the item that we're supposed to remove, right? That's why we have first dot equals X, right? And so if it is not equal to X, then we move that first back to the last, right? Because those are functions that we're able to use. However, if it is equal to the item that we're supposed to move, then, well, we've already moved first and we just don't do anything with that item. And so in the end, we're returning length doesn't equal size because we have the length, which is original size. And if we removed any items, then we're going to have a new size. And so if these two are unequal, that means that we have removed something. All right. And so as a quick recap of singular linked lists, as linked lists, singular linked lists have 2 pieces of data, an item and a next, can only be traversed in one direction. Doubly linked lists have 3 pieces of item, next, and previous. And finally, decks, they're implemented using both arrays and doubly linked lists, and use sentinel node to keep track of first and last nodes. So on the test, what you should expect to see, a lot of the time you're going to see a problem which looks very similar to practice 1, which is just kind of jumping through hoops and understanding what tail and head represent in similarly linked lists. You're also most likely going to see at least one problem which deals with decks. However, that problem is not going to be really about implementing it. It's more so going to use the tools that a deck provides you, which is to add last, add first, remove last, remove first, in order to solve a problem that would usually be very easy to solve using an array, but is a bit more complicated. So if you want more practice, I definitely recommend going to the CS61B website. Almost all of the midterms I looked at that Professor Hug has at least one problem that has deck. So make sure to do all those to familiarize with the topic. Any last questions? Yes. You. Right. So deck is a double-ended queue. That's just a fancy name that we give to a specific data structure that we implement using a doubly linked list. So like we can think of a deck as basically like a more complicated doubly linked list that has a few certain functions that we always implement for. It's an interface. Yeah, does that make sense? Okay, so it's basically like a deck is just like a doubly linked list. And then when we refer to a deck, we're saying that for that doubly linked list, we've implemented the functions add first, add last, remove first, remove last. No.
But what's the difference between this and we saw before, the int node?
An int node, okay, so well, I guess it depends on. Classically, no, single linked list will not have those definitions, but under, I guess, Hug's instruction, yeah, he said that you can implement those things in your SLLS class. So yeah, a deck is like Java's like formal version of that, but with a DLL list, if that kind of makes sense.
Yeah, but that means that like a doubly linked list is kind of more primitive than a single linked list. That's still use this method, doubly linked list doesn't, and the deck has the method. It's a bit confusing in terminology, but I guess it is.
Okay, I can look more in depth on this for you. Do you have a better explanation? I need to look at my computer for it, but obviously it's presenting. Yeah.
Right. So the way I would put it is that the int node is just how we implement a single linked list. A single linked list is just an idea that we have. It's an idea that we have a data structure that has nodes that are connected to other nodes in one way, right? And so when we implement a single linked list, there is no class called a single linked list, right? Because it's just a collection of classes that are nodes.
Teaches it as
Oh, Hug teaches it that way.
Yeah.
Oh.
And he teaches it as having those methods.
Darn Hug. Okay.
Yeah, so I think that's yeah, I can check
see.
that for you. I can respond to it in the ed post. I need to look at that. Unfortunately, Hilfinger's been teaching for the last few semesters, so it's very different from what it was last semester.
I see.
Yep.
In the back. Yes.
No.
Wait, what?
Not under Hug, not under Hug. Yeah. Yeah, I'll have to look more in depth at the specific definition, difference between those two.
I think there's like no more as a possibility for all. But how are arrays doing that?
Like to explain that?
Well, I don't believe arrays are used in deck, but did Hug implement it differently? Oh, I see. So generally speaking, right, you are able to implement a deck using both arrays and doubly linked lists. Just for the purpose of this class, usually we look at decks implemented using doubly linked lists. So, yeah, you can do it. I believe it's 2019 or 2016. I'm not entirely sure. Look at chat real quick. Right, so. All right, looking at this question, what does item signify? So this is something that you guys haven't learned yet, but basically that just means it is referring to any kind of data type. So that could be an int, a string, something that you define yourself. It's just a placeholder term, basically. Project 1 is not in the scope for the midterm. It's just that this was from previous semester. For the last problem, could we also create a new list and only add items that don't equal X? No, because the question specifically specifies that you are not allowed to use the new keyword. And that's in order to, that's just an extra constriction that is on you as part of the problem. Oh yeah. Oh, this person responds. Thank you for doing that. What is item first equal remove first set first equal to? So the remove first function removes it from the list and returns the item that was first in the list. And so it sets the item first equal to the first item that got removed. Why is there a first equal x in the if condition statement since we already had first dot equals x? I believe that is just redundancy. I don't think you'll be marked off if you don't have that.
Oh, one thing about the
And
difference between DEX and a DLL list, I can check it for you, but I don't think it's something that you should really worry about on the exam because DLL lists will be defined differently in different places. So they will tell you, they will say, okay, we're defining a DLL list as being this, such and such. Same thing for DEX. So they'll give you some like base information about what the differences are. So you're not expected to have like some like concrete idea of what it is going in because it's going to vary depending on how you're defining it. And they'll tell you how they define it on the exam. Yeah, go ahead. If you're within the class, you don't have to say this stop. You can say this stop, but you don't have to.
Also noting, they're saying on the chat that when you speak, could you like move closer to the computer?
Oh,
Yeah,
sure.
you're slightly unclear when you speak, but yeah.
Sorry.
Okay, that is it. Moving on.
So now I'll be going through recursion. So some of you may have some experience with recursion if you've taken 61A, but the reason that we're like sort of re-emphasizing it is because it's like sort of a fundamental like problem-solving technique that is actually used to implement many of like the data structures and algorithms you'll see in this class. So yeah, let's get started. I'll first just go through quickly what recursion is. So recursion refers to the technique of making calls to a particular function within its own body, often to compute like smaller subproblems. So yeah, over here I've defined like a very short and simple recursive function. Basically, it computes the arithmetic sum from 1 to k. For example, like 1 plus 2 plus 3 all the way to k. And yeah, we can see that this recursive function and most recursive functions have like three main building blocks, basically. The first is the base case, right? And for this function, it's if k is equals to 0, right? And the reason we need a base case for all recursive functions is to make sure that we don't have an infinite loop, basically. And then the next is the recursive step, which basically is the call within its own body, like often to a smaller input. So in this case, we are making a recursive call to sum of k minus 1. And then the last step is the like additional work we need to combine the smaller subproblems to achieve like our final result. So in this problem, it's just, you know, taking the result of the recursive call and adding k to it. And so that links up all of the all of the calls together, and that is what can give us our final result. So like recursive algorithms are like great for hierarchical data structures like trees and linked lists. And what hierarchical sort of means is that, you know, you can imagine like in a tree node, you have branches and branches reference other tree nodes. And then linked list, you know, every linked list node has a dot next or like dot tail, which references another linked list node. Yeah, so here's another recursive function. It basically sums all the values in a singly linked list. And yeah, it assumes all the values are integers. And yeah, it's like if when you're given a problem about linked lists, it's like a very natural process to like call the recursive function on the linked list dot next function. And the base case is just when the linked list is null. So we'll just like jump right into a like practice problem. Sorry if you can't see the top of the page. But yeah, but this is from spring 2022. And oh. Yeah, so on the left, you will see a definition for an int list class. This is like similar to the int list node that was discussed about previously. Yeah, and the question, I can just read it out, is fill in the definition of the non-destructive move to end and extract methods to meet their specifications. Do not add semicolons, do not use the ternary operator. And yeah, below they've given you like some doc test / examples. And yeah, so for the move to end function, it takes in an int list and split, and it just returns the result of moving all elements of L that are greater or equal to split so that they follow all elements that are less than split, maintaining the original order of the elements that are greater or equal to the order of those that are less non-destructive operation. Yeah, so that was like a mouthful. But don't worry, like I'll give you guys some time to like sort of digest the methods. And the next one is extract. So it takes in like 4 arguments, okay, like an endless L, split, a Boolean, and another endless rest, right? If GE is true, return the result of prepending all elements of L that are more than equals to split to the list rest. If GE is false, return the result of prepending all elements of L that are less than split to the list rest. And again, the operation is non-destructive. So I'll give you guys like 3 minutes to just look through the problem and try to understand it. You don't necessarily have to like complete the problem. Because of time constraints, I'll just start going through the problem after about 3 minutes. Okay, sorry, let me just get this out. Okay, there's a question. Unfortunately, you are not able to find the spring 2022 exam anywhere. I just have it because I took the class in spring 2022, so it's like a small little bonus. Okay, I will now be going through the question. So, okay. Yeah, first things first, like let's figure out exactly what move to end and extract do, right? So we'll start with move to end. Move to end takes an int list and an integer and returns a new int list with like basically some of its elements rearranged, right? All elements that are greater or equal to split are moved such that they come after the elements that are less than split. So like if I give you this sample list L, right, it has like 7 elements, and then I define split to be 5, we can see that yeah, we can see that like these highlighted elements in red are the ones that are greater than or equals to split, right? And then like what we expect our return value to be is this new int list such that 8, 5, and 6 are sort of shifted to the back of the list, basically. Okay, meanwhile, extract takes in an int list L, an int list rest, an integer split, a Boolean GE, and then it returns a new int list that adds some elements of L in front of rest, basically. Sorry, this slide just keep popping up. Yeah, if GE is true, elements of L that are greater or equals to split are prepended. If GE is false, elements of L that are less than split are prepended. So this is again an example, like if we're given L as this 7-element list, we have split equals to 5, GE equals to true. So we're looking for elements of L that are greater than equals to split, which is again 8, 5, and 6. And then we're given rest as like this 2-element list, 9 and 7. And we expect our result to be a new int list, which is basically 8, 5, 6, followed by 9, 7. And again, L and rest are unchanged. So at this point, does anyone have any questions about what move to end and extract do? Okay, cool. Yeah, now let's try to fill in move in, move to end. So we can see from the skeleton code that move to end basically just involves like two calls to the extract function. And like it further hints that the first extract call should generate the back half or like the last part of our result, right? So if we are given this example input, and then our last part will be 856, right? Because that is the part that should be like shifted to the back. And then finally, our final list will be something like 1, 2, 3, 4, followed by 856. Yeah, and the way that we sort of fill this in is as follows. Like, just imagine like last part, right? We want to extract the elements that are greater or equals to split and like sort of separate them. So we do this by calling extract on L, and then we supply split, except our GE is true because we want to take the elements that are greater or equals to split. And then for our rest list, like we just enter null, right? Because we don't want anything behind those elements. And then finally, like we call extract on L and split again, but this time our GE is false, right? Because we want to extract the elements that are less than split and sort of put them in front of last part, which now is the rest argument. Okay. Sorry, these slides are all messed up. Okay, so now for extract, like extract is a recursive function. And so like, let's start with the base case. If L is null, well, there's nothing to prepend, right? So we just return rest. Yes, and then in typical fashion of like recursive linked list questions, we want to like sort of process the head of the list, right? Or like the first element of the list, and then sort of recurse on like L.next or L.tail, for example. So we can see that the skeleton code kind of gives us a hint that we should split up into two cases, right? With our understanding of the function, like one case must be if the head fulfills the condition to prepend it, right? And the other case is if the head doesn't fulfill the condition, in which case we just ignore it. Yeah, so like to sort of formalize our intuition, let's take this sample list L and write out both what extract L will return and what extract L.tail will return. So we can see that, okay, if we're given L, extract of L5 true and null will give us 856, right? Just as we would expect. And then if we're given L.tail, which is basically L, but the first element cut off, if we call extract on L.tail, it will still give us the same exact answer, which sort of tells us that, okay, if the first element doesn't fulfill this condition, we sort of just like want to ignore it and then return whatever our recursive call is. Yeah, so we can fill in the last line as follows. Yeah, so if we ignore the first element, we just return whatever the recursive call returns, which is extract of L.tail, split, GE, and rest. Okay. Yeah, but what about if the head of L fulfills the condition? Then we want to prepend it to whatever is returned by the recursive call. So again, I have the same sample list L. If we run extract on L5 false and null, we want to extract, 1, 2, 3, 4, right? But if we call the function on L.tail, like since it has the 1 chopped off, like if we call the function on L.tail with 5 false and null, we basically expect to get 2, 3, 4, right? But not the 1. So that kind of gives us a hint on like how to combine these two like return values together. Yeah, and we do it like this. We return a new int list where its head is L.head, and the rest is basically the return value of the recursive call. Okay. Yeah, and the last thing to do is just to fill out the if condition. And note that since GE can either be true or false, we need to have like 2 distinct conditions. One is if GE and L.head is more than equals to split, more than or equals to split. And the other is if GE, not GE basically, and L.head is less than split. Then finally, we just use like an OR operator to combine these two conditions together. Like this. And yeah, now we're like pretty much done with the question. So at this point, does anyone have any questions about like how I approach this problem in general? Yes.
The first slide of it was like the implementation of the list, but I was just confused, like for the public business in head 0, what is like this head goal do? Because it's not like a good dot.
Sorry, let me just navigate this. Okay. So yeah, what was your question again? Sorry.
There's like a list with
Mm-hmm.
and then it says like this parentheses head 0. It's not like a this dot. So like does that operate?
Yeah, okay, great question. And like this is just referring to like calling the constructor, like the constructor that is directly above it. You see public int list head 0, tail 0, but supplying head 0 as the first argument and null as the second argument. Like I wouldn't worry too much about this syntax because it's like just kind of like a shorthand. Yeah, but like basically this is just calling the constructor. Yeah.
Does that make sense? Yeah, it's just calling like create a new instance. So it's as if you were saying new inlet.
Okay, I think there's some questions in the
Wouldn't be new, it would just be inlet. Yeah.
I think there's some questions in the chat. How many minutes on the exam do we get for this type of question? That's a good question. Like I think it depends. Because for everyone they have their strong topics and weak topics. But I would say around like 10 minutes on this sub problem because there are still like other parts of this question. But I say for this part, like definitely the challenge comes in understanding like exactly what's going on. And that can take you like maybe you have to read it like multiple times. So don't worry, you're not expected to solve this within like 5 minutes. It can probably take like 10, maybe at most like 15 minutes to like, yeah, approach this. Okay. For the else if condition, should we just check L.head more than equals to split? equals to GE. That is an interesting way to go about it. That I'm just trying to think. That could work, definitely. But yeah, and that might be like a little more creative way to approach it. But like in the test, they didn't give us any sort of restrictions on how we can structure our like this if statement. So I just chose to be more like explicit in like specifying exactly what conditions will be correct. Okay, another question, should we bring our own scratch paper? Like, I'm not too sure because CSM is not really affiliated with like core staff and exam
You
logistics.
would bring your own scratch paper.
Okay. And the last question is, when will the recording be posted?
Whenever it loads from my computer.
Okay, there you go. So, okay. That is it. I will now pass the time on to the next section. There are a lot of slides, right? Okay. Oh, sorry, and this is just a quick recap of recursion. Like I've included some common patterns for recursive calls and like a general guideline for solving recursive problems. Like you might want to put this on your cheat sheet if you find it useful. But yeah, thank you.
All right, hi guys. So now we're going to talk about nested classes. This will be a bit of a lighter topic, so let's just get started. So just to start off with the definition, nested classes are exactly what they sound like. They're just classes within classes. And kind of like we mentioned at the beginning of the presentation, classes will always have like these access modifiers in their method signature. So any class, even if it's within another class, will have this like public or private. So once again, yeah, the classes can be public or private, and public means anyone can access it when they are running your program, even in other classes. Meanwhile, private means that only you, the programmer, can access the code within the class. And this just helps a lot with abstraction, because if you're trying to like do something within a class, it's like a building block for that, but you might not necessarily need that outside of the class that you're currently in. And lastly, static means that you only use variables within your own like nested class. So it doesn't use anything from like outer classes. But yeah, we'll talk a little bit more about this later, but there's like a little table there that you might want to note. It was pretty helpful for me when I was taking the exam. Yeah, so here's kind of a more concrete example. I think this was actually taken from the lecture slides, but once again, nested classes just help construct like a larger class, like the int node for the singly linked list. And yeah, so here's kind of like an example in code for you guys to visualize that. And it gives you, the programmer, just more control over the creation and design of your classes and the data structures that you use. So I'll just leave this slide for a little bit. If you guys want to like note down this example, I think it's a pretty good example for nested classes in general. Yeah. Mm-hmm. Mm-hmm. Oh, no, I don't think we actually go over like package protected and stuff like that in this course. I think you can mostly just like note the public and private. Yeah. All right, so I'll just move on. So yeah, here's just another way of showing like instance versus static. Again, we'll talk about this in the next subtopic, but if you guys want to note this table down, it's helpful for me because I'm a visual learner. So yeah, go ahead and like take a picture or whatever you might need to do. This is also available online. So okay. All right, so now we're just going to do a question. So this one is kind of split up into these two parts here. But what you'll be doing is you'll kind of be going through down here and just noting like what the print statement will be. So take like 3 minutes and then we'll just go through it like line by line together. Okay. Also, really quickly, someone asked, you can have nested classes, but you cannot have nested methods in Java. Can you clarify what you mean by nested methods? I don't really know what that means. And then someone else said, what does it mean for a variable like first to be public or private? Yeah, so if you have a variable that's public or private, that just means you can access that variable like outside of the class or only within the class.
So an example of what that might mean for a variable. So if we have, let's say we have like a int node that has a private variable first. If I in main say b equals new int node, and then I try to call b dot first, main will tell me, sorry, I can't access that. That's not going to work. I'll get a compile time error. But if it's public, then I can't access it. If it's private, it means that I can only access it if I'm in the int node class, like making a new int node or whatever.
Yeah, so I'll actually go over kind of, this example kind of covers that as well. So just for the sake of time, let's just start going through this line by line. So yeah, when I'm working with these problems, I usually just like doing it literally line by line. So let's start off with this first one here, where it's asking us to find the result of system out print of y dot primitive. So what we want to do is we first want to go to y, and we see it's instantiated with rest equal to x, p primitive equal to 9, and then x dot reference is the reference, and then the slogan is eat. So right away we'll find like primitive, which is y dot primitive, and that will be 9 here. And then kind of going off of that logic, in the next line, when we're finding y dot reference, once again we use the same thing, where we go to the reference in this instantiated line and we find its x dot reference. So when we go to x, we see that reference was listed as new integer 7. So that's why we have 9 and 7 for these first 2 lines. So is that clear? Yeah.
How is it able to do that if the primitive and reference is private? So how would it do like the dot?
Yeah, so you're actually still within this class right now, if that makes sense. So you are able to access, because it's private just means that you can access it within the class.
Okay.
Yeah. Cool. Does anyone have any other questions at this point? Oh, check the chat. Okay, like for this example, you have public int list 5000, but you cannot have the following: public static void disinterbulate method be inside public int list 5000. Let's see. I think usually you would keep like the class and then the method like separate. So let's see. I think in this case, public static void disinterbulate is inside public class or public int list 5000. Yeah. When you write methods in Java, when do we need to write this method name, and when can we just directly use the method, assuming that it's called on the current instance. Yeah, so once again, like that would be depending on the access modifier. Okay. All right, so just to quickly go through the rest here. So next we see that we called like int list 5000 dot disinterbulate on Y. So let's quickly go to disinterbulate and see what that does. So when we're calling it on Y, we see that disinterbulate takes in an int list 5000 type, which Y is. So then we set Y's primitive to be 5000, and that will give us that next line here. So once again, just taking it line by line. And then as we see as well, disinterbulate also sets the reference of Y to be 1000, which is why we get 1000 down here. So is everyone clear on why that is? Yeah. It is, yeah. Okay, so after this, then we call Y dot indoctrinate on 100. So we go down here and we see indoctrinate takes in an integer. It sets that to be 0, and then it sets rest dot primitive to be B or 0. So what that means here is we have Y dot indoctrinate. So what we want to do is we actually want to take the rest of Y. So let's reference what Y's rest was. Y's rest is going to be X, and then we set X's primitive to be B, which is 0. So that's why calling X dot primitive gets us 0. That one was a little harder. Does anyone have questions on that? Yeah. Yeah. Yeah.
Why doesn't that change the Y?
P equals let me see. I think it's because this like main method is still running, if that makes sense. So it's kind of like referring to Y still as that. Am I correct? Oh, no, you're good. She asked like in disinterbulate. So the very third line is like you're setting P to be a new int list. So she asked like why that didn't change like Y itself, because disinterbulate is called on Y.
Yeah, I mean, yeah, because you're passing. So when you call, sorry, let me.
Yeah.
When you call a method, you're passing in the pointer of the variable. You're not passing in the variable itself. So you have like a P points to some like address in memory, which has like something stored in it, right? When you say like method of P, what you're doing is you're saying, okay, I want you to take in the pointer. You're not actually taking in P, and you're not actually reassigning the pointer at P. Does that kind of make sense? You can reassign what's at that pointer though, but you're not going to reassign what P points to, if that makes sense.
Yeah. Do you have a follow-up?
Yeah. Yeah.
Can you explain again how you got like 0 for the or what is the
Yeah. So when we call Y dot indoctrinate, right? So we go into this right away and we see B is set to 0, and then, or the variable P, once again, kind of like what she was referring to. Oh, sorry. And then what we want to do in indoctrinate is we want to call this dot rest dot primitive equals B, right? So this would be like Y in this case, because that's what was passed into indoctrinate or called on indoctrinate. And then we go to Y and we find the rest of Y. So as you can see, like y up here, the rest of it was x, right? And then we go to the primitive of x because that's this dot rest dot primitive. And then we set that to be, we set x's primitive to be 0. Does that make sense? Okay, awesome. All right, so just to go over the last two. So after this line here, then we call x dot integrate on new integer 200. So what that does is we go into integrate here and we set the reference of x to be 200. So that's why we get this line here. And then this last line is a bit tricky. So now we call int list 5000 dot slogan, and that gets us relax. And the reason why is because earlier, as someone pointed out, like we called new int list on this line or this variable. We set that to be new int list 5000 null 510 relax. And basically what that does it'll change everything like within these other variables up here, because every time you call int list 5000, it kind of like resets all of these. So that's why we get relaxed for the last line. Does anyone have questions on that? Yeah.
So since static or slogan is a static variable, if you were to call slogan on like x or y, would they also be relaxed? Or no?
Slogan on x or y. So static should be yeah, you only access like class variables and methods. So yeah, that would change just every time you call it. Yeah. Okay, cool. I'll pass it off to the last person.
Hi, hello. Can you guys hear me over Zoom?
Okay.
Okay.
Oh, and one thing, just to add about the whole reassigning P. If we were working in C, that would actually cause a memory leak because you're assigning something that we no longer have a reference to once we return the method and we're done with the method. Java though loves us and is very nice about memory, and it takes that P that's not accessible to us anymore and says, you're not accessible. The programmer can never find you again. I'm going to delete this because it's no longer useful. But if we were in C, it would cause a memory leak because we now have a location that we're using in memory that we have no way of accessing, which is problematic because we're using memory that we can't use or even delete. So yeah, Java's nice. We're happy that Java does memory stuff for us. Okay, so this last one is going to be presented on Zoom, but I'll have the hopefully full volume on my computer's enough because like I said, the mic is not working. Yeah, there are subtitles though. Allison, would you like to go ahead?
Yeah. Hello. So in this final section, I'll be going over static versus instance methods and variables in Java, and we'll also go through at the end a few simple conceptual practice problems to see how they work in practice. Next slide, please. So the main difference between static and instance methods are that static methods belong to like a class itself, whereas instance methods can only be invoked by instances of a certain class or like a specific object that you instantiate. So that said, static methods are invoked with a class name. For example, if we define a dog class, we could call dog.makeNoise, given that makeNoise is a static method. On the other hand, instance methods are invoked with a reference to a specific instance. So for example, if we instantiated a new instance of a dog called D, then we could call d.bark on it, given that bark is an instance method. And the same logic applies to variables, where static variables are accessed using class names and also instances, and instance variables can only be invoked using specific objects. Next slide. So now we can take a look at this example. On the left, we've defined a static method, and we know it's static because of the static keyword in the function signature. We can call this method with dog.bark, where dog is the class name. On the right, we define an instance method. So we have to define an instance of a dog in order to call this method. So we do that and call it Maya. In our instantiation of Maya, we define its weight in pounds, which is 100, so that when we call Maya.makeNoise, it goes to the last else statement and it's going to print woof. One important thing to realize here is that only instances of dog will have the attribute weight in pounds, which means that static methods cannot access a class's instance variables or methods. That's why the static method make noise can't access weight in pounds. The reason for this is that the dog class itself does not have a weight. Only specific instances of the dog have a weight, which happens when we instantiate them with our constructor. Another thing that's a really small subtlety is that you actually can access static methods and variables from an instance. It just doesn't work the other way around. So you can't access like instance methods from the static class. So yeah, I'll pause here. Does anyone have any questions so far? Okay, cool. Can we go to the next slide?
Oops, 1 second. Yep.
Yeah, so now we'll look at like a complete class implementation and also some practice problems. So I guess like first what we can see here is that classes are generally made up of both static and non-static actions. So in this class, we have a static variable binomial, which tells us that all dogs are of type Canis familiaris. We also have an instance variable, weight in pounds, which tells us that each instance of dog that we create will have a weight, and our constructor is where we initialize this weight. Finally, we also have a static method that takes in 2 dogs and outputs the heavier of them, and also an instance method that takes in a dog instance and outputs make noise based on its weight. So I'll give everyone like 1 to 2 minutes to go through these examples, and then I'll review the answers after that. Okay, cool. So hopefully that wasn't too challenging. So if we go to the first one, dog.binomial, what we notice is that binomial is a static variable, and we're calling it on the dog class. So that should output Canis familiaris. For the second one, dog.makeNoise, well, dog is the class itself, and makeNoise is an instance method, since we don't see static in the function signature. So that's going to error because, as we already know, static classes cannot access instance methods. And then we instantiate a new dog called Mindy with a weight of 20. So when Mindy makes noise the first time, it should output bark because 20 is less than 30, and its weight in pounds is 20. Then we increment Mindy's weight by 30, so now it's 50, which means that when Mindy makes noise again, it should output the last clause in that function. So it'll say woof woof. And then next slide. Okay, yeah, and then I'll give you guys like, go back 1 slide. Yeah, so I'll give you guys another 1 to 2 minutes to do these 3, and then we'll go over them. Okay, could we go back to the last slide really quickly, actually? Because I think there was a question in the chat. Yeah, so dog.binomial would output Canis familiaris, right? Because the dog is the class name and binomial is a static variable. Dog.makeNoise is going to error because here we're calling an instance method on the class name. And then we instantiate Mindy. Mindy.makeNoise is going to output bark because Mindy's weight is less than 30. Then we increment Mindy's weight by 30, so now it's 50, which means that when we call Mindy.makeNoise again, it'll output woof woof. And then there was a question in the chat that says, what would happen if we changed make noise to static? What would dog.makeNoise do then? So in this case, that there would be an error because if we made it make noise a static function, it can't actually run since weight in pounds is an instance variable, right? So like we can't compare that. in this case. Yep, we can go on to the next slide then. Okay, yeah, so again, 1 to 2 minutes for this one, and then what would be the answers? Okay, before we go over the answers, I think there's another question in the chat about like whether Java default initializes variables. So it does like initialize inst to 0, but the only problem here is that, or like even if you have like a dog class, like the fact that it's the class itself and not an instance automatically means it doesn't have like a weight in pounds attribute. So even though like it is initialized to 0, since dog is a class and not an instance, it's still not going to have that attribute regardless. Okay, so, or we actually did dog.make noise in the previous slide, so I'll just skip over that. But for dog.weight in pounds, so again, weight in pounds is an instance variable. So the dog class cannot access that, so that line's going to error. And then we instantiate 2 dogs, Cindy and Mindy, where Cindy has a weight of 20 and Mindy has a weight of 50. And so since max dog is a static method, we can call max dog on the dog class to compare Cindy and Mindy. Because Mindy is heavier, it's going to return Mindy. So when Mindy makes noise, since Mindy's weight is 50, it should output woof woof. And oh yeah, so there's another message in the chat. Why does weight in pounds have a parenthesis at the end? That was just a typo. So pretend there's no parentheses after weight in pounds. Okay, and then again, the other subtlety I mentioned earlier is that Java syntax allows you to call static methods from an instance, which means that it's possible to change static variables from an instance if you do so from a static method. And when you do so, it's going to change the value of the static variable across the entire class. So say, for example, I had a method like public static change by nomen, and it takes in a string. And I call like Mindy dot change by nomen on canis looper, which is like a wolf. Then it's going to change the binomen variable to canis lupin or looper for like all instances of dog that you call afterwards. So like essentially like what that meant to say is that you can change the value of a static variable from an instance, and it's going to change that value for the entire class. Yeah, any questions so far? Okay, in that case, we'll go to the last slide.
1 second, we have one question from the audience. Go ahead. So the answer would be, this would be an error. There would be no answer. Yep. Okay, go ahead.
Okay, next slide. Yeah, so we'll do this last practice problem. Given this new class dog, we have 5 calls here. So I'll give you guys like 1 to 2 minutes to identify which of these lines are going to error. Okay, this one is pretty short, so hopefully that's enough time. So first we initialize a dog called Papa. Papa.bark should not error because Papa is an instance and bark is an instance method. Dog.bark will error because again, you cannot call a static, or you cannot call a static class on an instance method. Papa.runFast should be fine. So we're allowed to call static methods on instances. And finally, dog.runFast should also be fine, since we're calling the static method on the class name. Yeah, so that'll be it for the static versus instances question or instances section. Thank you.
We have a question. Yeah.
So with the dog, also equals new dog, like that, like error because there's no public dog.
We're pretending it's there. Just assume it's there. Yeah, but that's a good catch. The question was, would dog Papa equal new dog not error because we don't have a dog constructor? The answer is we're just pretending that it exists. All right, yeah, question? I mean, yeah.
Like if you don't get any constructors, Java will create one for you.
Okay, there you go.
Is a constructor.
I didn't know that. There you go. Okay, so the other answer was even if we didn't have one, Java will create a default constructor for you, which has no variables, so it would still not error even if we didn't have a constructor. All right. Okay, so I think in that case, we're done. Thank you so much and good luck. Some of these slides you might be able to put on your study guide. Highly suggest that. And yeah, any final questions about anything? Yeah? They are in ed right now. Okay, great. Good luck, everyone. I hope you do well on the exam. I'll upload the recording on Ed if anyone's still here. Okay, bye.